Hello, my name is Dr. Zachary Roman, and thank you for joining me for the Multilevel Modeling course. Today we will be covering a review of regression analysis. It's important that you have a strong foundation in regression analysis moving forward because multi-level modeling will greatly build upon the framework. Our goal for today will be to quickly cover simple regression, multiple regression and assumptions. We'll look at partial and semi-partial correlations. We'll talk about inferential tests and p-values. We'll talk about some problems in regression analysis, and then look at some extensions for things like categorical effects via dummy coding, interaction effects, and curvilinear relationships. So let's start with linear regression. Regression is one of the most commonly applied quantitative methods and has been thoroughly investigated. In regression analysis, we look at the relationships between an outcome variable y and a set of predictors x. An important aspect when we have multiple predictors is that correlations between these predictors are taken into account, and this allows us to identify unique or redundant predictors. More on that later. So let's start with simple regression. Simple regression will frequently be depicted with a scatter plot, where we have the predictor x on the x-axis and the outcome variable y on the y-axis. Our points here are plotted with their associated x and y values, and a regression slope in the blue line there provides us with the relationship between the variables. Now let's represent that mathematically. So for a regression model for subject I, notice we use the I subscript here. So y subscript I is the outcome value for case I. We have beta 0 plus beta 1 times x sub I. So this will be the x value for the I participant or case. And then we have epsilon I, which is an error term, sometimes called disturbance or residual. The predicted value for this case is given by the same formula, but without the error term here. So our beta 0 is called the intercept, and beta 1 is called the slope. And epsilon I is the residual term or the error term for that case. Now notice that the error is the prediction subtracted by the actual score. So let's take a look at an example here. If this participant is case I, it looks like their observed y value is about negative 2.2, maybe 2.1. However, if we look at their prediction, given their x value here, their predicted value will be about negative 1.3. The distance between their observed score and their predicted value is epsilon. This is the unexplained portion of the variance here. And that's what's represented here. And we compute it by simply subtracting the distance from the prediction to the observed score. Estimation. In statistical models, estimation is the process by which we produce the unknown parameters in the model. So here we have beta 0 and beta 1. Those are unknowns that summarize the relationships between the x and the y. And we need to know what these values are. In simple regression, ordinary least squares, OLS, is the process by which we estimate these values. The betas are estimated using this least squares criterion. So what does this say here? Well, epsilon I squared is the squared error term here for case I. And so what we're saying is we want to sum all of the squared error terms. We see this here going up to n for every individual. So the sum of the squared error terms, or the sum of squared residual, provides us with a means of understanding the amount of error we have. Ordinary least squares achieves the best estimates of the betas by minimizing this value to its lowest potential value. When this is at its lowest, the other estimates of the betas are at their most optimal value. So let's take a look back at the scatter plot. If you imagine the slope of this regression line changing here, so turning, what we're considering here is each value has some unexplained variance, unexplained information between its prediction and its observed score. All of them do. Here we have an example where a case's observed score and predicted value are identical. What we want to do is this regression line twists until we find the optimal value where all of the sum to error is at its lowest. At that point, we know we have the best fitted regression line. That is the process that ordinary least squares takes to find the optimal values of the slope and the intercept given the parameters, or given the data. So we actually estimate 3 parameters in this model: the slope, the intercept, and the slope, as well as the variance here of the error term. After estimation is complete, we can compute something called R squared, which provides us with the proportion of variance of Y that can be explained by the predictor X. Here we have that. We'll talk more about R squared and how we compute that later. So let's interpret the model parts. B0 is the intercept, and it is the expected value of Y when X equals 0. B1 is the slope. For a 1 unit increase in X, Y is expected to increase by B1 units. Now, of course, if B1 is negative, it would decrease by this many units. Sigma squared epsilon is the residual variance that cannot be explained by the predictor X. And R squared is the percentage of variance of Y that is explained by X. Let's look at an example. If Y is the yearly salary in Swiss francs and X is our predictor years of education, if we have an intercept of 10,000, we would interpret this as meaning a person with 0 years of education is expected to make 10,000 Swiss francs a year. If our slope B1 is 5,000, for each additional year of education, a person is expected to make 5,000 francs more. And of course, R squared, if it equals 0.12, we would say 12% of the variance in salary is explained by years of education. Now let's look at multiple regression analysis. In multiple regression analysis, we add as many predictors as we want into the model. Here, we represent that with P. We will have P predictors and P slopes associated with those predictors. If you're familiar with linear algebra, we can also represent this in matrix notation. Notice where bold symbols represent matrices here. So the estimation of the betas using the least squares criterion presented earlier is conducted by applying the formula X transpose X inverse times X transpose Y. The X transpose X term includes the sum of squares and cross products of the predictor variables from which the covariance matrix can be derived. This is another way of saying this term takes into account the relationships between the predictors. X transpose Y includes the sum of squares and cross products of the predictor variable with the outcome Y, from which the covariance between the predictors Y can be derived. Again, this is another way of saying the relationship between the X variables and Y is taken into account. We will always estimate P plus 2 parameters. That is because we will always have an intercept and a variance of the residual term, leaving us with P slopes added. Here I have an example for you to work out. I won't talk through all of this math here, but this should put some of this into perspective for you on how the math works out. Notice that will result in the same values whether or not we do this in scalar notation, one at a time, or by solving in matrix notation. And here are resulting slopes, intercept and slopes from the predicted value formula here for the parameters. So now our interpretation changes. Let's take a look at how it works in multiple regression. In multiple regression, interpretations of slope parameters are now conditioned on all other predictors in the model. So we have our same example, but now X1 is years of education and X2 is IQ. Let's say we have an intercept equal to 3,000. A person with 0 years of education and an IQ of 0 is expected to make 3,000 francs a year. For the slope of education, if we have, again, 3,000, for each additional year of education, a person is expected to make 3,000 more francs when IQ is constrained to 0. This part is important. Because we condition all predictors on all other predictors, we can only talk about the unique contribution of a predictor when all other predictors are constrained to 0. B2. If the slope of IQ is 500, we would say, for an increase of 1 IQ point, a person is expected to make 500 francs more when years of education is constrained to 0. Notice again that we must condition the interpretation of each predictor relative to the constraint of 0 on all other predictors. So if R squared is 8.18, we would say 18% of the variance in salary is explained by IQ and years of education. Let's talk about some assumptions in OLS. Assumptions are important in statistical models because the models do not take into account some pieces of information. So we must assume it is true for the inferences and decisions we make from the model to be correct. Normality. We assume normality of the residual variable. We assume it is normally distributed with a mean 0 and some known variance. This simply says that the unknown amount of information cases have is evenly distributed across the prediction line, essentially saying we need to be equally accurate or inaccurate at predicting scores low on Y and high on Y for us to be able to make valid inferences. Homoscedasticity. This says that the variance of the residual does not change across different values of Y. This is again telling us that the predictions need to be equally accurate or inaccurate across the entire space of the predicted values. Linearity. By default, the relationships must be considered linear. Because we're using the general linear model of regression, we assume that the relationships between x's and y's is linear. If we have a curvilinear effect, this can be taken into account, but we must accommodate this with certain changes to the model. Without those changes, all effects are assumed linear. If they are not linear, then the parameters that we have will not accurately represent them. We also assume that there is no correlation or covariance between the error term and the predictors. This can cause problems of variance inflation and other issues with our estimates. Therefore, the unexplained variance should not be correlated with the predictor variables. Finally, the IID assumption. IID means independent and identically distributed. Subjects are assumed randomly sampled and independent from one another, stemming from the same distribution or population. This is very important, and a classic example of a violation of independence is when you accidentally sample spouses or roommates. Because these people have things in common with one another, and the model cannot take that into account, we assume that it does not happen. Violations of independence can lead to severe bias or improper estimates of our parameters. These things must be defended either methodologically or checked after the fact. We call that diagnostic testing. We will cover some of this in our course. If you're familiar with ANOVA analysis, then this section will make a lot of sense to you. We can partition the variance, well, we can decompose the variance in a regression model by making three terms. A sum of squares total, SS is sum of squares total, sum of squares regression, and then sum of squared residual. Let's take a look at sum of squared residual. Remember, the formula for an individual's residual is going to be their observed score minus their predicted value. Here, we square and sum that. So we have the sum of squared of the residuals. Here, we have the sum of squared regression. Here, we're taking the predicted value, subtracting it from the mean of y, again, summing and squaring, the sums of squares regression. Together, summing both of these, we have sum of squares total. This is the overall sum of squares. These can be looked at as raw proportions of variance. Sum of squared residual is the raw sum of square of unexplained information, where sum of squared regression is the raw sum of explained variation, and sum of squared total is all variation. This is useful because we can compute our square with this information. The proportion of variance in y that can be explained by all predictor variables is simply the explained variance over all variance. R squared can also be known as the coefficient of multiple correlation, because simply we're looking at the relationship here, or the covariance, between the predicted values and the observed values divided by all of the variance in y. Both of these will result in the same value. Tangentially related is the partial correlation. The partial correlation is a correlation between two variables conditioned on a third variable. The partial correlation of y in x2 conditional on x1 is given below. Here, we have the correlation R between y and x2, ry2, subtracted by the correlation of R with y1, and R, the correlation of y and x1, and the correlation of x1 and x2. On the bottom, we have the correlation of y and x1 squared, and the correlation of x1 and x2 squared, subtracted from 1, square rooted, and multiplied. This formula here provides us with the partial correlation of y and x2 conditioned on x1. Typically, this correlation is smaller than a normal correlation, so for example, between y and x2, because we're partitioning out variance from x1. So that is the partial correlation. Now we can also have a suppressor variable, which a third variable will result in a higher correlation than between y and x2. Let's take a look at the semi-partial correlation. The semi-partial correlation is similar to the partial correlation. However, the semi-partial correlation here is given by the same numerator as in the partial correlation. However, now we no longer partition out the correlation of y and x1. Notice that that's the only difference in this term here. So functionally, the difference between the partial and semi-partial correlation is that the impact of the third variable, here x1, is either removed from both or only one of the variables. So here, we are not partialing that out in the semi-partial, but in the partial, we are partialing that out. So that is our difference here. Let's talk about the increase in R squared. Depending on the pattern of correlations between predictor variables, the increase in the R squared can be high or only very small, depending on the correlations between the predictor variables and the outcome. The R squared for 3 predictor variables in a sequence is the sum of the 3 squared semi-partial correlations. So here, the R squared for a model with y predicted by x1 and x2, it can be derived from the semi-partial correlations. Here we have just the partial correlation, just the correlation of y and x1, the correlation of y2 semied with x1, and then the correlation of y with x3 partialed for 1 and 2. Depending on how strong the variables correlate, the inclusion of further variables leads to a different increase of the total explained variance. So here I have 3 correlation matrices for us. Under 2 and 3, x3 explains 49% of variance. Because the correlation here is 7, R squared, 0.7 times 0.7 is 0.49. So 49% of variance explained. The inclusion of the remaining variables, x1 or x2, only increases the R squared under situation 2. So we see that the difference in the correlation between x1 and x3 changes the amount of impact that the inclusion of those predictors have on the overall increase in variance explained. What is a suppressor effect? Well, a suppressor variable only correlates marginally with an outcome, so weak with y, but strongly with another predictor. So it is strong with another x value variable, but weak with the outcome. However, the increase in the R squared when including a suppressor variable into a model is high because the semi-partial correlation is high. The suppressor variable removes random noise of the other predictor variable. This can be useful. Useful suppressor variables are typically situation-specific or fluctuating variables that impair the reliability with which the other variables can be measured. So for example, we might predict school achievement from vocabulary tests and nervousness. However, nervousness might have a weak relationship with y, but a strong relationship with the vocabulary test, leading to a notable increase in the R squared. So let's review interpretation of regression coefficients in multiple regression one more time. The interpretation of each beta is always in reference to the other predictor variables. For each unit increase in x, y increases by the slope amount, while all other predictors are held constant at 0. The estimates for betas are only valid within the actual set of predictor variables. Their size or even sign changes if other predictor variables are included in the model. A model with 3 predictors should not be compared to a model with an additional predictor and assume that we're making the same claims here. Every predictor added into the model changes how we interpret all other predictors in that model. Now, because of this, we can't be making causal claims about the relationships between variables. However, there is an exception in a very specific context where causal claims can be made. And this is when we have some form of an experimental treatment, which is dummy coded for. It must be randomized, of course, and follow all good practices, best practices. But in this rare case where we're comparing the dummy coded effects of standardized random treatments, causal claims can be interpreted. Standardization of regression coefficients is important. People use this to make comparisons between scales on the same variables. So the standardized regression coefficient for the Jth predictor can be given by the standard deviation of x divided by the standard deviation of y times the slope. This provides us with standard deviations of change in our interpretation of model parameters. So when we say a 1 unit increase in x corresponds with a slope unit increase in y, when we have standardized our model, our parameters, we would now say a 1 standard deviation increase in x corresponds with an expected slope standard deviation change in y. This can be very meaningful when our scales are likely arbitrary, like with survey data and things like this. Let's talk about inferential statistics. The omnibus test for R-squared. The omnibus test is used to test the significance of the proportion of variance explained by the model. The null hypothesis for this test is that all of the regression coefficients, intercepts and slopes, equal 0. And that the R-squared value, in turn, is 0. There is no explanatory power of the predictors with the outcome. We compute this test statistic under an F distribution with the following formula with 2 different degrees of freedom. P being the number of predictors, and df2 is n minus p minus 1. Plugging it into this formula, we can compute an F value. We will compare an F value to our critical F value determined with a alpha threshold, and will provide us a decision on this null hypothesis, whether R-squared is equal to 0. We can also test subsets of predictors. This will be very important when we get to multi-level models. So we can test a single predictor or multiple predictors by testing the change in R-squared within a model. So if we have an unrestricted model with P predictors, and then we have a restricted model with less than P predictors, we can test the change in R-squared to determine if the inclusion of the additional predictors in the unrestricted model leads to a significant change in R-squared. This test is simply the same. We just now are testing the difference between the R-squares, and our hypothesis, our null hypothesis, is that the difference between the two is 0. Less functionally, this is interpreted as saying, we think the addition of additional predictors will not result in any increased proportion of variance explained. So we can test this again with an F statistic, which will allow us to make a decision regarding if the additional predictors led to a significant change in the R-squared. So for a data set with 5 predictor variables and an N of 100, a regression analysis results in a total explained variance of the dependent variable, an R-squared, of 0.25. The predictors significantly explain the criterion because, plugging in this formula, we have an F statistic of 6.265. Using an F distribution and an alpha value of 0.05, we can see that the critical threshold is 2.31. Because our test statistic is much greater than the critical threshold, our p-value is equal to 0.000046, which is thus statistically significant. So we can say that 25% variance explained is statistically significant from 0. Now, let's say we want to test if the exclusion of 3 predictors with small standardized regression coefficients leads to a significant decrease in the explained variance. So let's say with our 5 predictors in the model, 3 of them seem to be pretty low. Let's say we remove them and test to see if excluding them significantly changes the R-squared between the 2 models. So let's say beta 3, beta 4, and beta 5 are what we remove. The null hypothesis here is that all 3 of them equal 0. So the R-squared of the restricted model is given as 0.21. And so 0.25 is the unrestricted model. Using the change formula, we can derive an F statistic value of 1.67. Our F critical value is 2.71. And therefore, because this is lower, our p-value is higher than our critical threshold. And thus, the inclusion of those 3 predictors does not significantly change R-squared. And we could argue that the null hypothesis here is accepted. They are undistinguishable from 0 and thus not contributing significantly to the proportion of variance explained in the model. Now, using R-squared is one way to test the inclusion of predictors. However, we can also independently assess each predictor within a model using a standard error. So, it is derived from the regression coefficient and the standard error to determine this hypothesis. Our null hypothesis here is that the observed slope of predictor J is equal to the predictor J population slope. However, under the H0, we always assume this is 0. So what we're really saying here is the slope is assumed 0. The test statistic is given by dividing the observed slope by the standard error of the slope. The test statistic is t-distributed with a degree of freedom of n-2. Now, there are some assumptions regarding standard error estimates, and it will depend on multivariate normality of all variables in the model. If this assumption is violated, an over or underestimation can occur and lead to spurious results. So, how do we compute the standard error? The standard error is interpreted as the precision for which a regression coefficient is estimated. Another way of saying this is, it gives us an idea, given the information we have, how accurate our parameter estimate of that slope is relative to the population. If we have a high standard error, then we're not sure if that slope falls higher or lower. It's somewhere within that standard error. If it is a very tight standard error, then that would mean we have a lot of confidence that the slope estimate we obtained falls close within the estimate we have. And so, for simple regression analysis with a single predictor, our standard error formula is given, where we're simply dividing variance by the sum of squares of the predictor times our R-squared value, our inverse of the R-squared value. Squared, summed, and subtracted by 1. There is a more computing standard errors by hand in multiple regression is slightly more complicated. The textbook has information on this. Now, it is important to distinguish the standard error from the standard error of the estimate. I don't like how this wording is so similar, but these are 2 different things. So to reiterate, the standard error is a measure of precision around our estimate of the slope. It's a variance term that tells us how confident we are of our slope estimate. This allows us to make decisions regarding if the slope estimate is greater than or less than 0, or indistinguishable from 0. The standard error of the estimate, however, is a measure of the precision with which a prediction can be made, and it's derived from the variance of the residuals. So we're simply taking the sum of squared residuals, SS-res, these are identical here, dividing it by degrees of freedom. And this gives us the standard error of the estimate. Another way to think about this is this gives us an idea of what the average residual is. A high standard error of the estimate tells us that on average residuals are quite high, or our predictions are far from observed scores. A low standard error of the estimate suggests that predictions are close to their observed scores. So notice that the standard error of the estimate is used in the computation of the standard error. Let's talk about some problems of regression analysis and tests for their assumptions. One major challenge in regression analysis is a high correlation between predictor variables. This is often termed multicollinearity. Consequences of multicollinearity include unstable or small beta estimates. When we say unstable here, we mean when testing with other samples, if the correlation is present, the estimate could change quite a bit. And large standard errors. Both of these are undesirable and will lead to problems in decision-making in reproducing the results. Potential remedies. We can combine redundant predictors. If we think that two predictors are highly correlated, for example, shoe size in the Swiss convention and shoe sizes in the UK convention, this information is largely redundant and will show high correlations when looking at different shoe sizes. In the end, because they're so highly correlated, neither of them are really providing unique information. They're simply redundant. However, if we think that the correlation is high, but there's still unique information being present, we can actually combine predictors to make a single variable. We can just remove a redundant predictor variable, or there's alternative approaches which are slightly more complicated, which can allow us to estimate accurate, unbiased regression coefficients in the presence of high correlated predictors. We can test for multicollinearity using something called VIF, or variance inflation factor. VIF is given here. Each R squared comes from a regression in which xj is predicted by all remaining p minus 1 predictors. So simply, we produce a vector of R squared in which each predictor is dropped from the model and an R squared is produced. The VIF lays between 0 and infinity, and as a rule of thumb, if VIF is greater than 10, a multicollinearity problem is present for the respective predictor. So we will have a VIF for each predictor in the model here. Again, J and J. Alternatively, the tolerance is another estimate which can be used, which is just a reformulation of the VIF, 1 divided by VIF. You will see both of these. Testing for assumptions. If assumptions for the regression are violated, beta coefficients, their standard errors, and predictions can be spurious, as well as inferential decisions. Hence, the residual analysis is an essential part of the interpretation of a regression analysis. We assess normality of the residuals frequently with a QQ plot or histogram. This allows us to visually inspect whether or not the residuals are normally distributed. Homoscedasticity is assessed with a residual plot. We look at predicted values and residuals. What we're looking for is a constant variance across the predicted values of the residuals here. Linearity. We can just look at plots of the relationships between variables to assess for linearity. IID. The independence assumption is hard to test under some circumstances. We will discuss this concept of clustering in detail as it's critical to multi-level modeling. However, many times and in many analyses, we can't test this. Therefore, we need to simply methodologically argue for accurate sampling procedures which defend us against violations of IID. However, as we'll see, we can actually assess this given the right amount and type of data we have collected, typically data that is appropriate for multi-level modeling. We will be discussing this assumption in great detail as we go on with the course, as multi-level modeling can be a solution for issues here. What are partial plots? Partial plots investigate the relationship between y and each predictor x, from which influence of all remaining predictors is extracted. So we run a regression with x as a dependent variable, xj. We save the residuals from this regression and then plot y versus this predicted residuals. This plot should show a linear relationship. If this is not the case, we may have curvilinear relationships in the model which need to be taken account with other methods or modifications to regression. Note, interestingly enough, the correlation of y in the residuals is equal to the semi-partial correlation of y in xj, giving the remaining predictors, of course. Now let's look at outlier diagnostics. These are ways to assess if there are individual cases which might not be representative of our population, outliers, that are having a large influence over the regression results. Leverage is one way of calculating this. Information about how a different subject's predictor score is compared to the mean score. If you're familiar, they correspond to a squared Mahalanobis distance, which is a multivariate distance estimate. So the rule of thumb is that if leverage is greater than 2 times the amount of predictors plus 1 divided by n, it's an extreme value for subject I. Another way of putting this is, if the case has more influence than the average case, a large amount, 2 times more influence than the average case, then it is an extreme value which influences the regression line more than the average cases. Cook's distance is another way to think about this, and it has information about the change of the regression coefficient if subject I is deleted from the data set. So this is just another way of coming up with the same idea of this case is, when we estimate the model without the case in it, does the regression line change a lot? If so, then we know then that case has a larger influence over the regression line. These are things that should be considered prior to analysis and taken into account afterwards by computing these diagnostics. So let's take a look at extensions of regression to some specific things here. So we can use categorical predictors in regression via dummy coding. We can use product terms via interaction effects and polynomial effects for curvilinear regression modeling. Let's start with categorical effects. I will refer to these as factors. The categorical variables such as factors can be included in regression models by dummy coding them. For example, a dichotomous variable, let's say grad student or undergraduate student, we can code as either being 0 or 1. If we have more than 2, and this will be a single vector of zeros and ones. If we have more than 2 categories, we will need to produce a matrix. So for a categorical variable with k different categories, k minus 1 dummy variables are necessary. One category will be all zeros, and this is called a reference category. This reference category will be what all other variables are compared, or all levels of the factor are compared to. So the remaining categories will each be coded as 1. Now, advanced codings are possible, contrast and effect codings. This should have been covered in regression, and we won't do much of this in our course. So here's an example for you. If we're predicting the BDI, or Beck Depression Inventory score, from a set of treatment groups, placebo, cognitive behavioral therapy, psychoanalysis, and TMS, and we want to compare each of these groups to a placebo category, the dummy-coded matrix will look as follows. The placebo group has all zeros here. The CBT group has a 1 and then all zeros. And this follows for psychoanalysis and TMS. And so now, in this simple analysis where we just have this categories predicting BDI score, we will end up with 3 predictors in our model. We have the dummy code category 1, 2, and 3. So B0, or our intercept, is the average effect of the subjects in the reference group. Recall that the intercept says when all coefficients are 0, this is the expected value of y. So, looking at our dummy-coded matrix, when all of these variables are 0, we equal the placebo group. So, the intercept simply will tell us, in this circumstance, the expected value of y for the placebo group, or the mean of the placebo group on the BDI. Now, beta 1, 2, and 3 are the average deviations in BDI of subjects receiving each of the other treatments, respectively. So, dummy-coded group 1 here is going to be CBT. So this is a comparison of the mean difference between the CBT group and placebo. This is the mean difference between the psychoanalysis group and placebo. And D3 will be the comparison of the TMS treatment group and the placebo. We can derive the averages of each group by saying, well, because B1 is 3 units higher than the placebo's mean plus the mean of that group, B0 plus B1, gives us the average BDI for the CBT group. This is how we can make experimental comparisons across factors. Interaction effects, sometimes called moderators in psychology and the behavioral sciences. Interaction effects occur if relationships between variables change across different subgroups. For example, the relationship between previous math achievement and academic self-concept is stronger for boys than for girls. Or the relationship between intelligence and achievement in school changes with the engagement in school. The impact of stress on burnout is different depending on which resources someone has at his or her job. Interaction effects are differential effects, and interaction effects are operationalized using product terms. So let's say we have 2 predictor variables and 1 interaction effect is included. So our interaction effect here is, so we have our main effects, B1 on X1, B2 on X2, and then B3 on the product term, which is X1 times X2. Another way to formulate this is given below. The relationships between B1 star, X1 and Y changes across different values of X2 if the interaction effect B3 is different from 0. The moderating role of X1 and X2 is symmetric. Both variables can be viewed as the moderator variable for the relationship of the other variable with Y. It is a symmetric relationship. So, let's say we want to take a look at the relationship between X1 and Y. However, there's this, let's say we have a significant interaction effect with X2 and X1. This would tell us that at different levels of X2, the relationship between X1 and Y is different. And here we have an example of this. So when X2 equals 0, here's our slope between the relationship of X1 and Y. When X2 is high, say 2, the relationship is greater. And when X2 is low, the relationship between X1 and Y diminishes. This is the idea of interaction effects, and they are frequently employed in psychology to explore the complicated phenomenon of behavior. We will cover interaction effects in much more detail when we get to multi-level modeling. Curvilinear relationships. In order to test curvilinear relationships, there's many different methods which can be used. Parametric models, which will specify a concrete functional form, like quadratic effects, and non/semi-parametric models that will approximate an unknown functional form. So, as far as a known form goes here, we have the use of a quadratic effect. This is a parabolic relationship. So in this case, we have an intercept, a slope of our single predictor x, and now we have x squared. This will approximate a curvilinear relationship and will allow us to estimate nonlinear effects. Now we can also include cubic models or any higher order or exponential term to quantify the curvilinear effects here. While other approaches exist, such as splines and non-parametric approaches like piecewise growth models, we won't discuss this in detail here for regression, but they may make an appearance later in multi-level modeling. Thank you for taking the time to watch this regression review with me, and Have a great day.